This project is small Gradio application that tires handwriting to video in one flow. On one side, you write using touch or mouse, and when you hit recognize, it turns TrOCR, which is transformer-based optical character recognition model, to OpenVINO. So your strokes are converted into text and merged into the prompt text into the prompt box. So you can also type the prompt directly. When you click generate, the second component activates Lightricks LTX-Video, again through OpenVINO GenAI, exposed as intermediate representation with no separate PyTorch CUDA video path in this repository, which turns the text into a short MP4 displayed in the UI. TrOCR and LTX both run inference through OpenVINO on the Intel GPU XPU, not through the PyTorch CUDA inference path, while Gradio application connects handwriting OCR to text to video output. OpenVINO is Intel's toolkit for fast inference on Intel hardware. It takes models, converted to its intermediate representation, IR, and runs them with the OpenVINO runtime on CPU, GPU, and other supported devices. optimum-cli is the interface between the transformers, diffusers, sentence transformers, and trim libraries, and the tools and libraries provided by OpenVINO to accelerate end-to-end pipelines on Intel architectures. So how they relate? Optimum-cli is Python plus Hugging Face layer, while OpenVINO is the underlying runtime and intermediate representation format. So optimum-cli exports models to intermediate representation and drives OpenVINO interface. So you don't need to write low-level OpenVINO code for every model. We will come to this soon. The setup batch file is a first-time Windows setup script for this project. So it runs from the project folder, checks that Python is on path, creates virtual environment, and if it doesn't exist, activates that environment, upgrades pip, and installs requirements.txt. So export LTX Python, opens the project's YAML file and reads it. So the script copies the current environment and sets environment HF home, Hugging Face home to that HF home. So HF home is used by the child process and not by the Python's global environment. So this list represents the full command line passed to subprocess run. It runs optimum-cli to export the model to OpenVINO intermediate representation format. So CLI is the path to optimum-cli and exam Windows. Export is subcommand. It's convert or export a model. OpenVINO is target format. It's OpenVINO IR intermediate format. It's an XML and bin. We will see it. -m is model ID, which is Hugging Face model to load. In this case, Lightricks LTX-Video. Weight format is weight format that store weights as FP16. It's half precision. Library plus diffusers is treat the checkpoint as diffusers pipeline. LTX is diffuser style, so the exporter uses the correct loading export path. And str out there is the output directory. It's models LTX-Video F16, where the intermediate representation and related files are written. So it uses the optimum-cli to export Lightricks LTX-Video from diffusers into FP16 OpenVINO intermediate representation format under this output directory. When optimum-cli runs inside that subprocess, it uses Hugging Face Hub and related libraries with our AGF home. At that point, the library checks the local hub cache and avoids downloading files that are already present. So let's run it. So running here, HF home. So you see that it quickly shows 100% because everything is already downloaded and starts processing. So sub-process run starts optimum-cli as a separate process, waits for it to finish the OpenVINO export, and raises error if the program fails, like check equals true. So this export step can take some time. Let's stop it. Let's rename this folder. And start it again. So this time, instead of overwriting the files, it generates new folder and files. So now it will generate the files that XML and bins. So the Lightricks LTX-Video repository provides diffusers weights as safe tensors. And the command optimum-cli export OpenVINO converts the pipeline into OpenVINO IR intermediate representation format, which is XML plus bin. So we will see now XML bins generated. The OpenVINO LTX-IR intermediate representation conversion is finished. So now perfetching TrOCR weights. The setup is about to warm up TrOCR. We import YAML to read config YAML. Import OCR OE, the local OCR module, and parse the config into dictionary. This step is optional. Prefetch some octet so the Hugging Face weights are already on disk and any load errors appear during setup. It's not required for the app if you already have a cache. So OCR over init. So OCR over init from config. Runs in two places. Once in setup batch file as an optional prefetch we saw, and again when the app is running and every time you click it's recognized. On the first recognized click it takes some time to fully load. On subsequent clicks it reuses the in-memory model, which is very fast, as we will see. Init form configures the OCR section from config YAML. With which TrOCR checkpoint to use, whether to run on GPU or CPU. It also points downloads to our project's Hugging Face root via models HF home. The models Hugging Face. Then it calls load OCR. So the load OCR imports. It's TrOCR processor. It's from transformers. It handles image pre-processing and decoding tokens into text. And OA model for vision to sec from optimum-cli. It's the OpenVINO backed vision to text model, not standard PyTorch inference. This Quark cache there ensures that downloads and metadata go to your configured Hugging Face directory, modeled Hugging Face, rather than the default user cache. Here are OCR processor from pre-trained loads tokenizer processor files for the specified Hugging Face model, and OE model for vision to sec from pre-trained loads the same TrOCR checkpoint but runs it through OpenVINO on the selected device, CPU or GPU. Export through means convert to OpenVINO intermediate representation format if needed. The run batch file runs the Python application app.py. When you run application.py, you are starting a small web application in your browser. The library that builds the application, the forms, buttons, video player, and layout is a Gradio. It's made for ML demos. You define Python functions, Gradio wires them to buttons and shows outputs like your video on the page. When you click on the recognize button, Gradio calls on recognize function with the current sketch with this image editor value and the current prompt text. It returns the updated prompt string, which is the previous text plus new OCR, and the status string, empty on success, or an error message. In unrecognized, we first call init from config, which loads initializes the OCR stack from the global configuration, TrOCR plus OpenVINO, which we have already discussed in detail. Then it turns sketch into pill image. So Gradio image editor may return pill, which is a Python image library, or dictionary with composite background. Then it calls run OCR and returns new text, which we'll look into it later. Then it normalizes the current prompt via prompt value. So in combined is the in combined it's a previous and new text joined. New and previous and new text are joined with the space and we are dropping the empty parts. So success returns combined prompt text plus empty status, and on an exception it keeps the previous prompt text and put the trace back in status. Run OCR. Run OCR function. Run OCR defines function and input where input is an optional pill or none. An output string is recognized text. So load OCR ensures that TrOCR processor and OpenVINO model are loaded or reloaded if config has changed. We have already discussed it in detail. The process for TrOCR makes the picture RGB, puts transparent sketch pixels on white, and if it's still grayscale, repeats it to 3 channels so the model always sees the standard height, width, and 3 values per pixel RGB like red, green, blue channel image. The TrOCR processor turns the pill image into model inputs like pixel values and return tensors equals PT. It means that PyTorch tensors for the OpenVINO backed model. So OV model for Vision to Seek runs auto regressive generation, and output is token IDs for the predicted text like vision to sequence or image caption. And then it converts token IDs back to string. Skip special tokens through it actually drops padding beginning of sequence, end of sequence style tokens. And the 0 is the first and only sequence in the batch. So if Code returns non-fuzzy, treat it as empty, then strip leading trailing white space and return the final recognized text. Debug the application. You should install the Python debugging extension, and then create launch the launch JSON and settings JSON files which they generated for me via prompt. So let's start debugging. The first breakpoint I set was inside and generate a function when this recognize button is clicked. So I'm writing hello. Click on the button. So inside this load OCR, processor is the model level variable that was the Hugging Face rock processor for the handwriting OCR path. If we look into this TrOCR processor, we can see that there is an image processor that prepares images for the vision encoder for common TrOCR checkpoints. This is often with image processor style component. And OpenVINO, which handles text, vocabulary, special tokens, and decoding generated IDs to string. This model actually loads vision to sequence model. It's TrOCR image to text through optimum-cli. So inference uses the OpenVINO runtime instead of plain PyTorch for the generate path. This export through means in OpenVINO intermediate representation is not already in the cache. Optimum will convert the PyTorch model to OpenVINO intermediate representation once, save it under the cache there, then load it. If IR is already there, it reuses it. So the first run can be slower, just around 1 minute. Later runs are faster. Look into it, we will see the vision encoder decoder. So vision encoder decoder model is the Hugging Face architecture name for models that encode an image with the vision model. Encoder is often with style, and decoder is decode the text with the language model decoder. So TrOCR is implemented like this: image, encoder, decoder, then token IDs. So editor to pill. If you look into editor value, which is image editor, you see both background and composite are pill images. So background is the base canvas, for example, white empty layer. So composite is the flattened result, background plus brush strokes and any other layers merged the way the UI shows. So the order means use the merge preview if present, otherwise fall back to background, and otherwise treat the value as pill image directly. So now run OCR is called. So as we already called the load as OCR, this time it will skip it. So now I'm sure RGB white BG is called with pill image. So if the image mode is RGB, so those lines flatten transparency onto a white background. So TrOCR always gets a plain RGB image. TrOCR is trained on handwriting on light backgrounds. If you didn't composite transparent regions, they could turn back. They then could turn black or wrong colors and hurt OCR. White behind matches typical document style input. So this input is processor images equals img. That runs the Hugging Face through processor on the RGB pill image. The processor applies the vision preprocessing and packages the result for PyTorch. So input is a batch-like structure, typically including pixel values that can be passed straight to the model generate. So this step doesn't run the OpenVINO model, it only prepares tensors. If we look into inputs, we see input mainly holds pixel values for the tensor. The first one is one image is a batch size is one. Then three it's an RGB channels. Then heightened width after resize with pixels as normalized floats, not row 0 to 155 values. So this model generator runs TrOCR inference on the OpenVINO packed model. The inputs plug the processor output, mainly pixel values, into keywords arguments for generate. So generate does the heavy work. It's vision encoder plus autoaggressive text decoding. It repeatedly predicts next token IDs until the sequence ends. So this generate IDs is a tensor of integer token IDs, not readable text yet. The next line decodes them with batch decode. So OpenVINO runs the TrOCR model to turn preprocessed image tensors into generated token IDs. So the generated token ID is a 2D tensor. And here one sequence in the batch and 4 token positions. So this generated so the actually the generated IDs tensor lives on CPU and that's normal. So batch decode works fine on CPU and some stacks leave generation output on CPU even when the heavy model run on GPU or OpenVINO. So this batch decode uses the tokenizer inside TrOCR processor to turn integer token IDs into strings. Batch means it can be decode many rows at once. So batch decode returns list of strings, one per batch row. We only run batch size 1, so the list has length of 1. So 0 takes that first and only string, the recognized line of text. So we run OCR and get new text. That's what it read from your sketch. Then we look at the prompt box. If there was already something there, this is pref. We combine the two, usually pref plus new text with space between. If pref was empty, you just end up with new text. And now you see a hello in the prompt. When you open the application, you will see Gradio page. On one side, there is a place to draw, and on the other, you will see the video once it's done. Below that, there is a prompt box and 3 buttons. The sketch area is for handwriting. You can use mouse or touch. The brush starts fairly small and black. You can usually adjust the stroke size and pick a color from the editor's options. Is the standard Gradio drawing UI. Canvas is a fixed white strip, not an infinite page. There is full screen control in the editor, as well as open full screen, sketch, and close overlay buttons. So we use those to pop the sketch into larger overlay, making it easier to write. Same drawing, just more room. So if you zoom in on the sketch, you can usually drag the view around your hand so you are not stuck in one corner. So that's how the image editor tends to behave once you are zoomed in. The RAM of my HP Omnibook is 32 gigabytes. When I run this application, it uses only 16 gigabytes of VRAM. This can be seen in Task Manager and the performance in GPU, where the shared GPU memory shows about 16 gigabytes, and this was before the update. I checked my driver version in Device Manager. And it was 6973. I read that in version 6974 and above, they introduced the shared GPU memory override feature. The feature we are looking for is called shared GPU memory override. Intel introduced this specifically to address the exact problem we are having. Local AI models needing more than the standard 60% VRAM cap. On a 32 gigabyte system, this feature can let you allocate up to 87% of your RAM, which is about 27 gigabytes, to the GPU. If we open the Intel graphics application, you will not find an option to override it. Note that this is after the update, and the one before was considerably different. Updated I navigated to the Intel Arc graphics driver page. I downloaded the driver and installed the update. And after the update, Device Manager shows version 8531, which is the version I installed. So after that, when I opened the Intel graphics software and navigated to the graphics tab, I saw the option to extend the memory up to 27.5 gigabytes, and I enabled it. So after the update, I saw the shared GPU memory showing 27.1 gigabyte in Task Manager on the shared GPU. Now we'll experiment with handwriting in pieces. Each time we recognize, the new text is concatenated into the prompt. When we are happy with the full prompt, we will start generating the video. Because recognize click, it takes some time to fully load. Subsequent clicks, it uses the memory model, which is super fast as we'll see. Um, next. View, wait, um, shoot. Yes. Let's generate. Generating a 2-second video with the parameters we discuss later takes around 4 minutes. So this is the shared GPU memory. You can also download it. So the video will appear in the project's output folder. Let's debug the video generation. So I'm setting prompt and click on generate video. So prompt is car derives down a two-lane mountain road, and etc. The first breakpoint is set when the onGenerate function is called. So initial LTX, we make sure that the LTX pipeline is loaded before encoding the video. The function LTX-OV directory returns the absolute path to configure the OpenVINO IR model directory for LTX, resolving relative paths against the project root. So it's models LTX-Video FP16 folder. So OpenVINO GenAI's text to video pipeline. It loads the LTX text to video model from the exported IR folder. Just as a string path and binds inference to the device from the config, and default is GPU. So the result is stored in the module level pipeline. So later calls to generate LTX video can run the generation without reloading. So we call generate LTX video, passing the prompt, and the callback to track the progress of the video generation. So this block reads video generation setting from the model global config set when load pipeline run. It pulls the nested LTX dictionary, then assign local variable used later in generate LTX video. So the width and height, they are output resolution. Now frames, it's how many frames to synthesize, default 25. Now inference steps is diffusion steps. Guidance scale is how strongly the model follows the prompt versus creativity. Frame rate is frame per second when encoding, saving the video. It's negative prompt text telling the model what to avoid. The default string lists common failure modes like bad quality, motion issues, etc. Seed is affixed to 42 for reproducible randomness. Video CRF constant rate factor is optional edge 264 encoded quality. So lower CRF means higher quality larger files. So we call pipeline generate, which performs the full LTX text to video diffusion run with our resolution, length, sampling, guidance, seed, and progress hook, producing output for save video from GenAI. So it takes time, and let me pause it, and I will resume once the next breakpoint is hit. So output video is an OpenVINO tensor holding the decoded video date. Save save video from GenAI. We write the generated video frames to a file, which is an MP4 at the given path.